So we're going to go over chapter 21, and 21 is just all about metallic bonds. So the way I'm kind of going to break this down is I'm going to explain to you why metallic bonds are happening, kind of more on the atomic level, and then we're going to go on and we're just going to talk about what you kind of need to know for the test. So the 4 properties of metallic bonds, and then just one chart that's kind of about metals, and we're going to talk about semi-metals a little bit, and then that is all you really know for chapter 21. So when just starting off, metallic bonds only happen when you have 2 metals coming together. So it happens when metals and non-metals come together, okay? Another good thing to know is that we call metallic bonds, another name for them is a network solid. So what happens is, let's just take sodium. So you have Na and you have an Na, and they come together. So what happens is that we know sodium atoms, if you go and you look on their periodic table, each one of them only has 1 valence electron. So they have 1 valence electron. So when those 2 orbitals come together, what they do is they make a brand new orbital, okay? That's why things bond, they make new orbitals. So they make a new orbital that's at a lower energy. So those 2 electrons come together in this new lower orbital, okay? But if we start out with 2 orbitals, we have to end with 2 orbitals. So we get 1 lower orbital and 1 higher orbital. Don't worry about why it happens. It's fancy chemistry that you do not need to worry about. We're just going to move on and say that they come together. So if you can imagine, if we just have thousands and thousands of sodium atoms all coming together and they each have 1 electron, all these orbitals are going to come together and they're going to start stacking on top of each other. So stack, stack, stack. Just, if you can imagine, layer upon layer upon layer until eventually there's no distinguishing, there's nothing distinguishing in between the 2 layers. So if you look in your book, that's why we get these, what we call conduction bands, okay? This band lower is called the valence band, and the higher band is called the conduction band. All the electrons go down and they fill up the valence band first. So that's why we get all the electrons down here. So because there's no difference between any of these different bands, the electrons can go to any band they want. So maybe an electron right here can go to a band up here, and it can go to an energy level or a shell that's up there. So I'm going to erase this. If you want to relook at it, you can rewind it. But pretty much what we get from this idea is what we teach you in class when we say a sea of electrons. Because the electrons can go to any orbital they want, they're just delocalized. So you have all these different positive nucleuses, and then you have all these electrons all around it, okay? And those electrons are delocalized. All that means is that they don't have to be with the proton. They don't have to be bounded to the proton. That's different when we talk about ionic bonds. So 4 characteristics come out of this, okay? So metals, you guys all know this. Metals are malleable, okay? You can bend a metal. They also are good conductors, okay? They're also shiny, and they are opaque. And I spell it wrong every time, so I'm sorry about that. Okay, they're malleable conductors, shiny, opaque, and they also they have high melting points, and they have high boiling points, okay? So it takes a ton of energy to take a solid metal and turn it into a liquid metal. So let's talk about it. You guys know that positive charges and negative charge repel each other. So if you can imagine, I take a hammer, and I start, let's say that I have a block of gold. So I take my block of gold and I take my hammer and I start pounding down on my block of gold. We talked about how protons are really, really massive. They're super, super hard to move. So these protons, okay, these positive these positive nucleuses, that's the right way to say it, they get closer and closer together, okay? We know that positive charges repel. So we don't want this to repel. So the electrons are going to come in because they're free to move. That's the important part. The electrons are free to move, so they're going to come in, they're going to buffer these positive charges coming together. That's why it's malleable. Okay, so why are they good conductors? Things are good conductors because electrons can flow freely through them. That's really all electricity is. It's a free flow of electrons. So if I go and I have an electric current, I just want to get this electron through. Because I have delocalized electrons all around, this electron can pass freely through because the delocalized electrons inside the metal will just move it through because they're free to move. So that's why they're good conductors. Electricity can be conducted because electrons will conduct it. They're shiny and opaque. So now let's imagine you have a photon. And this photon of light tries to come and it tries to go through this block of gold. It's like walking through a really, really, really crowded street. It's really, really hard to walk down a street if there are a bunch of people. You have to weave your way in and out. So the photon might come and maybe there's an electron and that photon hits that electron and it bounces right off. Okay, that's why a metal would be shiny. Now, we already talked about earlier how we had all these different valence bands, and then we had our conduction bands. We talked about how electrons, when they get energy, can jump up in energy. So, because an electron can jump to any band it wants, it can absorb any frequency of light it wants, any energy of light it wants. So, a photon could also come and just be absorbed into the metal. So that's why it'd be opaque. You can't see through it because those photons don't travel through it. So now let's talk about high melting points and boiling points. The only thing you'll get something to melt, or the only way you'll get it to boil, is if you start breaking bonds, or if you start breaking interactions between your positive nucleuses and your electrons. The nucleuses are really, really strongly positively charged. They don't want to be left alone. They don't want to have no charge buffering it. So if I go and I try to take an electron away from away from a nucleus, it's going to be really, really hard. That's going to take a lot of energy. So it's going to take a lot, so it's going to have a high melting point and boiling point because it'll be very hard to separate those two things. So that is these are the 4 properties of metallic bonds. You need to know these and you know why they happen. So one other thing that might be useful from this chapter is when we talk about semiconductors and we just talk about metals. So the biggest difference is that with metals, when we get this, we get no band gap. So metals, you get a valence band, and then you get a conduction band. But with semi-metals, so just really quickly, a semi-metal is our elements on that column. If you look at the periodic table, we tell you that there's a staircase. It's marked by a yellow line in your periodic table. They're just elements on either side of the staircase. So if you take any of those elements and you start putting them together, you get a different band gap. So when you use semi-metals, you get a band gap. Okay, why is this important? Because now if you want to take an electron, if you want to excite it to a higher energy state, you have to give it a certain amount of energy. So let's say I go and I give, let's say, this electron energy and I move it up to this band, okay? Well, electrons don't like to be at higher energy, so as soon as I stop giving it energy, it's going to come right back down. And we talk about in class, if an electron ever goes down in an energy level, it gives off a photon. So this is how LED lights work, okay? Semi-metals, LED lights. Moving on to, this is a resistivity chart. So pretty much that only means, or what that means is how well something is at conducting things when it gets to higher temperatures. So resistivity, another way to think of it is conduction. So metals, the hotter they get, the worse they get at conducting. Semi-metals are the exact opposite. The higher the temperature, the better conductors get at conducting things, or their resistivity goes down. That's why in your computers, we don't use metal chips. We use chips made of semiconductors because at high temperatures, they'll function better. So that's kind of chapter 21.